The first section of a roller coaster can be modelled by the cubic function h of x, which is equal to 1 divided by 4 times x cubed minus 15x squared plus 44x plus 60, where h is the height in metres of the roller coaster above the ground, and x is the horizontal distance in metres from the starting platform of the ride. This function correctly models the roller coaster for x as an element of 0 to 10, both included. For part A, we want to show that x plus 1 is a linear factor of h of x. If we think back to our factor and remainder theorem, we know that if x plus 1 is a factor, then h of negative 1 should equal 0. So we need to test that. So we have h of negative 1 is equal to a quarter times negative 1 cubed minus 15 times negative 1 squared plus 44 times negative 1 plus 60. And now if we simplify that, we're going to have a quarter multiplied by negative 1 cubed is negative 1. Negative 1 squared is positive 1, so we're just going to have minus 15. Then we're going to have minus 44 and plus 60. And hopefully you can see that if you do that sum, that is equal to 0. So we've shown that x plus 1 is a linear factor of h of x. On the CAS calculator, go into the main menu. The first thing I'm going to do is define the function, because for a question like this, we know that we're going to use it a fair bit. So we're going to type in 1 divided by 4, and then all of that is multiplied by x to the power of 3 minus 15x to the power of 2 plus 44x plus 60. Highlighting that, we can go interactive define, and we can call the function name h by going to the ABC keyboard and selecting h, and then pressing OK. So that's h of x now. For part A, we can confirm using the calculator that x plus 1 is a factor by once again evaluating h with negative 1 substituted in. So if we press execute, we get that equals 0, so x plus 1 is a factor. For part B, we want to use this information or a different method to fully factorise h of x. So for this, we're going to use synthetic division, and in synthetic division, we put the coefficients of all the polynomial terms. So we'll have 1 for the 1x cubed, we'll have minus 15 for the minus 15x squared, then 44 for 44x, and then positive 60 here for the constant term. And then out to the side, we're going to solve x plus 1 is equal to 0, which gives x equals negative 1, which is the value that goes here. And then we start the process. So we add down the first column, and we have 1. And then we have negative 1 times 1 is negative 1. Then we add down the next column, so we have negative 15 plus negative 1, which is negative 16. And then we have negative 1 times negative 16 gives positive 16. And then we have 44 plus 16 gives 60. And then negative 1 times 60 gives negative 60. And adding down the final column, we get 0. So there's a remainder of 0, which confirms that x plus 1 is a linear factor. So once we have that information, we can now say that h of x is equal to 1 quarter times x plus 1, so the linear factor that we already knew about, and then that is multiplied by, and then we use the values down here to work out what's in the next bracket, what the factor is, and this will be x squared minus 16x plus 60, so we use these values as the coefficients, so this is x squared minus 16x plus 60. And now using our knowledge of quadratics, we can further factorise this to say that h of x is equal to 1 quarter times x plus 1, and then we factorise that by inspection. So we're going to have x, and then we look for the factors of positive 60 that add up to negative 16. And you should note that we can use negative 10 and negative 6 to do that. So that's the fully factorised form of h of x. We can also fully factorise h of x using a CAS calculator. So if we highlight h of x, just the name, we can go interactive, transformation factor, and then factor. And this gives us the fully factorised form. So that is just confirming what we've already found by hand. For part C, accurately sketch the graph of h of x over the interval x is 10 to 10 included on the set of axes provided. Clearly label any axial intercepts and turning points with their coordinates correct to 2 decimal places. To sketch h of x using the CAS calculator, press the graph icon. That will bring up this screen, and now we can just drag h of x down, and that will graph the cubic for us. What we now need to do is resize the screen so that we can see all the key features that we want to. So we press the 4 arrows at the top, And we might set our x minimum to be -2, just a little bit before 0, and the x maximum to be 12, which is just a little bit past 10. And then our y minimum we might select to be -15, and the y maximum we might have as about 30. And we press OK, and that will graph for us. And now we can use analysis gsolve, and we can use these options to find the key features. So y-intercept will give us the h-intercept of the graph, and pressing execute will lock that point onto the screen for us. We can then use analysis gsolve max to find the local maximum turning point up here. Once again, hitting execute will lock that there for us. And then analysis gsolve minimum will find the local minimum turning point. Hitting execute locks that on so we can refer to it later. Then we can use analysis gsolve root to find the x-intercept. So the first one's outside of our domain, so I won't bother locking that onto our graph. Clicking right, we find the next one's at 6, and then pressing right again gives an x-intercept at 10, and again hitting execute will lock that onto the graph for us. So our job now is just to copy what we found from the CAS screen onto the set of axes. So we start at 15, we go up to about 25, down through 6, and then up to 10. So that's a rough sketch of what our calculator screen had. Our h-intercept was at 0,15. Then we had a maximum up here that was at 1.79, 24.11, correct to 2 decimal places. And a minimum down here, which was at 8.21, -9.11, correct to 2 decimal places. We also had an x-intercept here at 6,0 and an x-intercept here at 10,0. And we use coloured in dots for our two endpoints here and here because those values are both included in the domain. For part D, we want to state the height in meters of the platform at the start of the ride. So from the graph on our CAS calculator, we can see that it's 15. And algebraically, if we evaluate h of 0, that's equal to 15 meters. So that's the height of the starting platform. We can confirm what we found in part D by evaluating h of 0, and pressing execute gives 15 meters, which is the height of the starting platform. For part E, we want to determine the maximum height in meters of the roller coaster ride, stating the answer correct to 2 decimal places. So on the CAS calculator, we can see that the maximum height is at 24.109. So we can see that the maximum height is 24.11 meters, and this occurs when the x value is equal to 1.79 meters horizontally from the starting platform. For part of the first section of the roller coaster, the ride travels underground. Determine the maximum height in meters that the roller coaster reaches underground. State your answer correct to 2 decimal places. Once again on the CAS calculator, we can see down here that the minimum value, so the maximum amount it goes underground, is -9.109. So the maximum height underground is a positive quantity, so it's 9.11 meters, and this occurs when x is equal to 8.21 meters horizontally away from the starting platform. For part 2, we want to determine the horizontal distances in meters from the starting platform where the roller coaster is at ground level. So inspecting the graph, we can see that the roller coaster is level with the ground at 6 and at 10. So from our calculator graph, we saw that x is 6 and x is 10 meters as solutions. Algebraically, that's the same as solving h of x is equal to 0. And again, that gives x equals 6 meters and x equals 10 meters horizontally from the starting platform. However, we can also use the algebraic solver in the main menu to solve h of x is equal to 0, and we can highlight that and go interactive equation inequality solve for x. So that gives x is 6 and x is 10 as the 2 points where it's at ground level during the first part of this roller coaster ride. For part 3, we're asked for what percentage of the horizontal distance is the roller coaster underground for the first part of the ride. We know that it first goes underneath the ground at 6 meters and then re-emerges at 10 meters. So it has a distance of 10 subtract 6 meters, which is a total of 4 meters underground, divided by the total length of the first part of the ride, which is 10 meters, and that is going to give us 0.4. Timesing by 100 to get a percent, we know that the answer for this is 40%. percent.